In this video, we're going to be looking at topic 7b, which is physical properties and how they're affected by intermolecular forces. And this is for topic 7 of Unit 2 of the Edexcel IAS chemistry course. So we're going to be looking at how we understand physical properties in terms of intermolecular forces, focusing specifically on boiling temperatures and volatility. We're also going to then look at how we determine how we choose a specific solvent, so whether we choose water or we choose non-aqueous solvents, and again explaining these in terms of intermolecular forces. So if we start off by looking at the alkanes, now remember the alkanes are homologous series of saturated hydrocarbons, and they have the general formula CnH2n plus 2. Now what we see when we look at these molecules is as the molecular mass of the alkane increases, the boiling temperature also increases. Now when we're thinking about alkanes, of course they are hydrocarbons, so they only contain carbon and hydrogen, so we're not going to have any hydrogen bonding and we are not going to have any permanent dipoles. So the only significant intermolecular attraction here are London forces. The more London forces that are present, then the more energy is needed to break those, and therefore the higher the boiling point. So we need to understand why, as we increase the molecular mass, our boiling point increases. So we can see that we have the molecular mass of our alkanes at the bottom here, and you can see this trend is that as we increase, we go from a gas at room temperature up to liquids at room temperature, and so on and so on. So our boiling temperature is increasing. Now the reasons behind this is because as the mass increases, your number of electrons is increasing. So remember, as you're adding mass, you're adding atoms. And when you add atoms, you are, of course, adding electrons. So the more electrons there are, the more chance you get your instantaneous and induced dipoles. So therefore, we're getting more and more London forces. We also get an increased amounts at the point of contact between the chains. So we're getting more increased instantaneous and induced dipole interactions between the chains. So you can see as we go from propane to butane to pentane, I'm getting more and more points of interaction between the chains. So therefore I must be getting more intermolecular forces. And the more London forces, the more energy is needed to break them. And then that gives us our higher boiling point. So anytime you're asked about boiling points, it is all to do with how many London forces there are, because that will then tell you how much energy there is. The more London forces, the more energy is needed to break those. Okay. Now, if we're looking at branching as well, then we see a trend of that our boiling points are going to get lower in comparison to our unbranched. So if we look at an isomer here of pentane, you can see that all of them are going to be C5H12. Pentane is your straight chain. Then we go to 2-methylbutane, which is one branch, and then 2,2-dimethylpropane, which is two branches. And you can see that we go from 309 to 301 to 283. So we are getting a decrease. And the reason for this is we get less packing of the molecules. So we're causing those points of contact to not be as close. So for example, if I have pentane, we can see that they will pack very well. If I take 2-methylbutane, you can see right away that they are not going to pack as much. So I'm losing the points of contact here. So because I have less points of contact, I'm getting less London forces. If I have less London forces, I need less energy, therefore my boiling temperature is lower. So you're always relating the amount of intermolecular forces to how much energy is needed to break them. If we look at a different homologous series, this time we're going to look at alcohols. So alcohols have the general formula CnH2n plus 1 OH. So because they contain this OH group, they are of course going to form hydrogen bonds as well as those London forces. Okay, so having this additional intermolecular bonding, so having the hydrogen bonds, causes an increase in the boiling temperature when you compare it to its equivalent alkane. So what does that actually mean? Well, if we look at our number of electrons and we compare them, so if we take methanol, methanol has 18 electrons, which is the same as ethane. If we compare the boiling temperatures, well, we can see that ethane is 184, so that's going to be a gas, whereas ethanol is 338, so that's going to be a liquid at room temperature. And if you compare each of them, so from 26 electrons, we're comparing 231 versus 352. For 34, it's comparing 267 to 370, and for 42 electrons, comparing 309 to 390. So because we have this hydrogen bond, which are stronger forces, we need more energy to break the bonds. So of course we're going to be increasing our intermolecular forces, causing our more energy, causing our higher boiling point. Okay, so this is explaining what we're just discussing there. So because we have the same number of electrons, if it was only London forces, then the boiling points would be identical. But because we have these hydrogen bonds, when we have methanol in comparison to ethane, methanol has a higher boiling point because we require more energy in order to break these intermolecular forces. Now, hydrogen bonds are the predominant bond, so the bond that has the biggest effect. That's what predominant means. And are short chain alcohols, but as they become longer chain alcohols, actually your London forces become the more predominant. And it is because the hydrogen bonds can only happen at the OH group. If you then increase the chain length, you're going to be getting large amounts of carbons and hydrogens, which have got London forces, and the larger amount of London forces you have from them are going to become eventually stronger than the hydrogen bond. So we can analyse this by looking at their enthalpy of vaporization. So we've discussed enthalpy in topic 6, and enthalpy of vaporization is the amount of energy required to completely separate moles of a liquid and convert it into a gas. So this is actually a direct measure of the strength of the intermolecular forces. So we can look at this and we can see how strong the intermolecular forces are. And you can see as we increase the chain length, going from ethanol to propanol to butanol and so on, our enthalpy of vaporization increases. And we see this as well in our alkanes, and it is because the London forces become more predominant. Okay, so they become the force that determines the boiling point. When we look at the hydrogen halides, again, boiling temperatures are affected by intermolecular bonds. So we're going to compare HF, HCl, and HBr and HI, so the hydrogen halides. And hydrogen fluoride has a much higher boiling point, and it is because this has hydrogen bonds. Okay, it is the only one of the hydrogen halides that has hydrogen bonds. For the others, so you see we have a large drop as we go down to HCl, but then we have an increase in our boiling temperature, and that is a result of the increase in London forces. So as we go down the group for the halides, we're going to get more electrons. Therefore, we get an increase in London forces. So that means that we need more energy to break the bonds. Of course, then giving us a higher boiling point. So in your answers, you should always be referring to the fact that it requires more energy to break a specific set of bonds, and that's why you get a higher boiling point. If we shift our focus now to water, water has two properties which are anomalous. So for a molecule that has so few electrons, it actually has a relatively high boiling and melting temperature. And the density of ice at 0 degrees is less than that of the density of water at 0 degrees. That is just another way of saying that ice floats on water. In theory, it shouldn't. And we're able to actually explain these by using the intermolecular bonding that is present in water. So if we look at the melting and boiling point first, water has very strong hydrogen bonds between its molecules, and it also has London forces due to the fact that it has 10 electrons. When we compare water to ammonia and hydrogen fluoride, they all have very similar London forces because they have similar numbers of electrons. So we would expect the boiling point to be the same. However, water has a boiling point much higher than the other two. Water's boiling point is 100, whereas hydrogen fluoride is 20 and ammonia is minus 33. Now, all of these have got 10 electrons, so they should be the same, but you can see it's potentially linked to the hydrogen bonding, but they all have hydrogen bonds. And actually, hydrogen fluoride has stronger hydrogen bonds because it's fluorine, which is the most electronegative. So why is water so much higher than hydrogen fluoride? And it is all to do with the fact that hydrogen fluoride can form 2 hydrogen bonds, whereas water can form 4. Okay? So if we've got 4 hydrogen bonds here, again, that's going to require more energy to break them, giving you a higher boiling point. So it's all to do with the fact that water will make more hydrogen bonds than hydrogen fluoride does, and the more hydrogen bonds it makes, the more energy is required to break them. And also, when you have hydrogen fluoride and you're vaporizing it, actually not all of the hydrogen bonds are broken, and it is because there is a level of polymerization between the hydrogen fluoride molecules, but you're not going to have to go into too much detail with that. Now, ammonia has the lowest boiling point because it can only make 1 hydrogen bond between the lone pair on the nitrogen and the delta positive of the hydrogen. So that's why ammonia is the lowest, then hydrogen fluoride, and then water being the highest. Because here we can make 1 hydrogen bond, hydrogen fluoride can make 2, whereas water can make 4. And as I've said a few times now, the more hydrogen bonds it can be made, the more energy required to break them. Now, when we're looking at the density anomaly, it is to do with the fact that the molecules in ice are arranged in rings of 6 that are held together by hydrogen bonds. So you can see that we've got our water molecules being held in this sort of cyclic structure. And this is because, if you remember, hydrogen bonds are at 180 degrees. So they're going to be held in this rigid structure. And what that does is it creates large open areas of space inside the rings. And because it has that large open areas of space, we're packing less molecules into a specific volume. So therefore, our density is lower. When we melt the ice, that ring structure is destroyed because we're breaking those intermolecular forces. That causes the molecules to move closer, and we get an increase in density. So ice has a low density, and that is due to that ring structure, whereas water has a higher density. And because ice has got the lower density, it allows the ice to float on water. And it is all to do with the fact that the hydrogen bonds hold it in place. So let's now pivot to the second part of this topic, which is looking at suitable solvents. So for a substance to dissolve, there are two conditions that have to be met. Your solute particles have to be separated and then surrounded by your solvent particles. And the forces of attraction between the solute and the solvent have to be strong enough to overcome the forces of attraction between two solute particles or two solvent particles. In other words, if your solute is stuck together and the force of attraction is so high that it doesn't want to come apart, it will not dissolve. So we have to make sure that we pick a solvent that will overcome these forces. So if we have an ionic solid, it is going to be able to dissolve in water. Okay, you learned this back in GCSE, now it's just the explanation of it. And this is due to the hydration of the ions in the lattice. Now you will talk a lot more about this in topic 12 and A2, but we're just going to go into a little bit of detail here. So what happens is the delta negative end of your water molecule, remember water is going to have our dipoles like this. They're going to attract the sodium ion, and they will attract it enough to remove it from the lattice. So if I was to take, I'm discussing sodium chloride, if I was to put sodium chloride into water, the delta negative end is going to attract the sodium and pull it out of the ionic lattice, and we call this an ion-dipole interaction. Whereas the delta positive end of the water is going to attract the chloride ions, and they are then surrounded by the water molecules, and they are held together by hydrogen bonds. And we call this process hydration, and we get a specific amount of energy released, and we call that the hydration energy. But as I said, we're not going to go into a lot of detail about that just now. So what does this actually look like? Well, you can see here that we've got our ionic lattice, and we have our water molecules. And the water molecules are starting to arrange themselves in a favourable position. So you can see our delta positives are going towards our chloride ions at the top, whereas the delta negative end is going towards the sodium ions at the bottom. And eventually what will happen is the attraction here will become so strong, it will pull apart, and it will then cause the ionic lattice to break. Your chloride ion will be surrounded by water molecules with the hydrogens being closest to it, whereas the sodium will be surrounded by water molecules with the oxygen being closest to it. Now, alcohols can form hydrogen bonds with water, so ethanol and water will always mix with each other. Okay, so because we have this hydrogen bond available, we're going to get this attraction being overcome, so we can always mix this. Now, the solubility of alcohols is going to decrease as you increase your chain length, and that's linked back to what we were saying earlier, is the fact that London forces become more predominant when you've got this long chain. If we compare that to non-polar molecules like alkanes, they are not going to be able to dissolve in water, and it is because the attraction between the alkane and the water is not strong enough to disrupt the hydrogen bonding between the water molecules. So remember, we said we had to break a solute-solute bond, but we also had to break the solvent-solvent bonds, and it's this one that is the problem. The hydrogen bonds between water molecules are so strong that the alkane, the attraction that it has, is not strong enough to break that hydrogen bond. So the majority of non-polar molecules are going to not dissolve into water, and there are some polar molecules that will form either no hydrogen bonds or very weak hydrogen bonds, and they will have limited solubility, and you'll talk about that in topic 10. So the general rule for choosing a solvent is like dissolves like. So non-polar substances will dissolve in non-polar solvents like hexane, and polar substances will dissolve in polar solvents like water or ethanol. So let's have a look at some past paper questions just to finish off. So this is some multiple choice questions from the January 2019 paper. So in alkanes, increasing the length and branching the carbon chain both affect the boiling temperature. What combination of effects is correct? So remember, if we have, let's say, this molecule of pentane, and then I compare that to butane, we know that the boiling temperature of pentane is going to be higher than that of butane. So increasing our chain length is going to increase the boiling temperature. So that means that we can ignore B and C. So our answer has to be A or D. Now if we take pentane again, and we compare that this time to a branched isomer, we know that the pentane is going to have the higher boiling point. So increasing the amount of branching is actually going to decrease your boiling point. So therefore our answer must be A. Question 6, we want to look at the correct order for the boiling temperature of hydrogen halide from the lowest to the highest. So we know right away that HF is the only one that has hydrogen bonds. So that is always going to be in the number 1 spot. Okay? Then we have to consider what the other forces are. And the other force that takes effect is then going to be your London forces. And remember, the more electrons, the more London forces. So if we remove the HF and we compare HCl, HBr, and HI, we have to look at what one has the lowest number of electrons, and that is HCl. So that's going to have the lowest boiling point, and the only one that has that as an answer is A again. And you can see both of them giving you an answer of A, and there's an explanation there as well if you want to have a read at that. So again, sticking with the January 2019 paper, this time going into the written part, the question is about the structure and properties of the alcohols ethanol and butan-2-ol. So we have ethanol, which will look like that, and butan-2-ol, which will look like that. Okay, and we want to think about all of the intermolecular forces that are present in these alcohols. So if you've watched the previous video where it's talking about the actual formation of the intermolecular forces, you will know that I gave you the tip that you should always write London forces. Okay, and then we have to think about what else is present. Well, the fact that we have carbons connected to oxygens and oxygens connected to hydrogens, that must mean that we have permanent dipoles. So we must have permanent dipole-dipole interactions. And lastly, because we have an OH group, of course, we must have hydrogen bonding. Now, part 2 is looking to explain why butan-2-ol has a limited solubility in water. So we've already said in this video that ethanol can dissolve in water, but why butan-2-ol then is a little bit smaller. So first of all, why is it soluble? Well, butan-2-ol can form hydrogen bonds with water. And that is because we have that OH group. So it allows us to have the hydrogen bond, which allows some of it to dissolve. However, when we have something like butanol, the London forces between butanol molecules are quite strong. Okay, so they start to become a bit more predominant at this point, and then they're quite strong, and they're actually stronger than ethanol. Therefore, that requires the amount of energy in order to break those to be higher in terms of the hydration. So remember, this time we're not talking about the actual breaking of the bonds using temperature, we're talking about the hydration. And it is because the London forces are more predominant as opposed to the hydrogen bonds in water. And again, you can have a look at the mark scheme for that if you want. And then the last question is looking at the January 2016 paper. So when chlorine is passed over iodine crystals, iodine monochloride is formed. ICl is a liquid at room temperature, whereas Cl2 is a gas. For 4 marks, we want to explain in terms of intermolecular forces why this is possible. So this has to be a compare and contrast question. So the first thing you have to do is you have to identify what forces are present in each of them. So ICl is going to have London forces, but it is also going to have permanent dipole forces, because we've got quite a large electronegativity difference between the I and the Cl. If we compare that to chlorine gas, of course, doesn't have any dipoles, and it doesn't have hydrogen bonding, therefore it only has London forces. Now, because ICl has 2 types of intermolecular forces, that means that the intermolecular forces in ICl are stronger than in Cl2, okay, because it has both the London forces and the permanent dipole forces in order to overcome. So we're going to need more energy. There's also the fact that, for the 4th mark, London forces in ICl are stronger than London forces in chlorine, because ICl has more electrons. So it's all about explaining which bonds are stronger, or which one has more intermolecular forces. And that gets you your 4 marks, as you can see from the mark scheme. So that's everything for topic 7b, physical properties. If you've got any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.